Okay, so yeah, I am Tejun. I work at Meta in the kernel team, and I'm going to present about schedext. There are like a lot of disagreements about how to pronounce this, but I'm sticking with mine. So, okay. So what is schedext? So who knows what a scheduler is? Yeah, cool. So I mean, like a scheduler is that if you have a machine, you have CPUs, right? Then you have threads that you want to run, right? So there are n threads and m CPUs, and you kind of have to map them somehow, right? That's what scheduler does. Sometimes you have more threads than your CPUs, sometimes less. You still have to decide which CPU runs which threads. So that's what scheduler does, right? And it's the CPU scheduler. Who here knows what BPF is? Cool. Yeah, a lot. Okay. Yeah. So BPF, in really short, is like a way to write code, and you kind of compile that into like a bytecode, and then you upload the kernel, and the kernel verifies that it's safe to run, so that the machine is not going to crash by running that, and then it runs that, right? So that's what really short what BPF is, and then it allows you to do a lot of things. So earlier. In the early days, most of the use cases were around networking, right? So if you get a packet, right, if you run a really small program really quick before much of the networking stack has run, then you can do a lot in terms of packet filtering, manipulation, DDoS protection, and all those things. So that's where BPF started. But over time it gradually got more and more and more generic with more capabilities. And schedext is like a new application of BPF where you can upload these BPF programs, which implements like a full CPU scheduler in BPF. So you write your code, your scheduler in BPF. You build the binary which contains that BPF bytecode. You run it, and which almost the BPF blob to the kernel, and kernel replaces the kernel scheduler with your BPF code. So that's what in short what schedext is. So if you want to write a scheduler, like what does it look like? So this is a really simple an example, probably overly really it doesn't really do much. So what it does is that it implements a global FIFO scheduling. Which is just a fancy way of saying that in the whole system we're just gonna run whatever wakes up early the first on whatever CPU which becomes available the first, right? I mean, it's barely any scheduling, right? It's a really simple thing. But I mean, this is how you write it. So you have like in queue, which gets called when a thread wakes up. So you queue the thread to the scheduler, and there's a dispatch which gets called when the CPU becomes available. Right, so the CPU becomes available. It's now looking for a task to run, a thread to run, and that's what gets executed. And then there's the init, right, which initializes the scheduler. And then there's the ops, right? The ops struct is just kind of binding them together and then telling schedext that this is the scheduler. Right? I mean, load this and use this as a scheduler. And as you can see, this is as simple as it gets. Whenever something wakes up, we put the thread in a queue called DSQ global. It's just like a simple like a convenience queue, which can be either FIFO or an arbitrary priority queue. And then whenever the CPU becomes available, we just consume from that queue, right? I mean, that's what it does. It's but you can see how easily you can implement a scheduler, right? So if you do this and if you run that binary, your whole system will be running on that scheduler. And so how does it look in practice? It's just it's just a capture from my my terminal. So I mean, it's not the prettiest, but I was too chicken to do this live. So bear with me. So there's a file called the syskernel debug. It has moved. So this is a little bit outdated, but there's an interface file you can cat, which shows you the current state of the schedext. I mean, is it loaded? Is it then what's loaded, right? How many threads is it managing all these things, right? And so at the beginning it says that enabled 0, right? So it's not enabled, nothing is loaded. Your system is still running a default kernel scheduler, which used to be CFS, is now EVDF, right? The fair class scheduler. And you run then your own binary called extensible. Let's say that's what you built from the previous code, right? The really short thing, which is extensible is an example scheduler, which is in the kernel tree and also the public SCX repo. But it's a little bit more complicated than that because it also implements like a B-time scheduling. But it could as well be just global FIFO scheduling, and it would be that short implementation. So if you run that, it just prints out some statistics, right? I mean, there's like local 16 whatever whatever the scheduler decides to say about it, and then I Control Z, right? So I just stop that user process, and then I kept the status file again on the right side, and it says that this object is loaded and is enabled, it switched all threads and all that, right? And then I continue. So this is just showing you that they're switching the scheduler to schedext, the scheduler that you wrote or somebody wrote and you built. It's just as simple as running this binary. You run this binary, you switch to that scheduler, you kill that binary, then you switch it back to the current default scheduler. So is it safe or useful? So this is on our flat on our so we have a lot of different services, and some of them are like really big, and this is one of really big services. And here the service is mostly latency bound, and so if you can make tail latency more consistent, you can process more. Your bandwidth goes higher because the machine is not fully utilized. It's bottlenecked on the latency. So if you make it go a little faster or more consistent, then you can do a little bit more work, right? Within your set, I don't know, time deadline. So if you make your scheduler work a little bit more consistent, then you can see your RPS goes a little bit higher. So there are like two different sets of lines, but basically they are both bandwidth lines. They're just reading different signals from different points in the pipeline. And the green line is what I'm experimenting with, right? The orange line is the control, and the vertical marks are when I'm loading different schedulers with different parameters to see what works better. So what I'm here trying to show is that if you look at the first cluster of lines, right? That's me switching scheduler like every 2 hours, every hour or every 2 hours. So I load up something, I try to read some signal, and then it doesn't look too good. Then I try something else and something else and something else, right? And then after that day, I set on certain parameters and certain implementation. Then I let it run for 1 day, and after that day, I change it to I tweak it a little bit, and I just keep doing that over multiple days, right? That's what it's showing. And you can see that the green lines sometimes are higher, sometimes it's lower, right? I mean, so I am kind of exploring what actually works for the workload. So the thing is that for this workload, it takes I don't know, setting up the experiment takes like a week, right? At the shortest, right? I mean, and the minimum machine that I need to set this up is maybe like 1,300 machines. That's like a bare minimum I need to get any kind of signal out of it, right? So if I didn't have access to schedext, I couldn't, so each time I want to change something in the scheduler, I want to reboot all the machines, right? I need to deploy new kernel, reboot all the machines, and set up the experiment again, and then get them going again, and they have to now warm up, right? Then you verify them against control. So that would take at least 3-4 days, if not longer, right? Each iteration. Instead, right, just 1,300 machines, I set it up once, and I dynamically change scheduling as quickly as I can get signal, right? So you can see how quickly, how much easier it'd be to experiment with scheduling policies, right? I mean, what works for a specific workload. Right. So and in one of those lines, one of the early lines, on the first day, like one of those concentrated lines, some are just policy tweaks, and others are code changes, right? So I change code, I deploy the scheduler, and it sometimes just crashes, right? I didn't write good enough code, and then it looked okay on my really simple test. When I deployed to 1,300 machines working production workload, they just fail, right? What happens then? So what happens is that the BPF code fails, it errors out, whatever, but then the system statefully reverts back to the system default scheduler, and on top of that, it captures the system state and then dumps it. So to tell you why it failed and where the threads were at the time of failure and what the scheduler was doing, right? So that to help you understand why it failed and to debug it. So this is an example from SX QMap. QMap is another like a fairly simple example scheduler. And if you do like a -T100, it just tells that after scheduling 100 threads, right, just skip one thread after 100. So it's inducing an error condition where it's just dropping one thread, through the cracks, and see what happens. So you run that, and it runs for a while. It prints some statistics, and then it triggers the debug dump, right? I mean, it says that one of the threads didn't run for over 5 seconds, right? And the timeout, there's a hang check timer, which triggers if a thread which woke up didn't get scheduled on a CPU. So it triggers and it tells you that this thread was woken up 5.8 seconds ago, but it didn't run. It didn't actually run. So I am aborting all this and reverting back to the safe kernel scheduler, right? And then it shows what the backtrace was, and then on each CPU which tasks were queued, and what their states are. So you can, well, not always easily, but it helps you understand what went wrong. And then the system is completely fine, right? I mean, my scheduler crashed multiple times while development. The workload was just running just fine, right, the whole time. So with this, are we seeing any gains? So it's just dreaming into the in the previous graph is just dreaming into like a shorter timeline, and then it's the green line seems higher, right? So we are still verifying the results because that depending, we have like multi-region data centers, and depending on the region, the workload is a little bit different and all that. But I mean, we seem to be seeing at least on this metric, like 4, maybe close to 5% gain, which is huge for us, right? If you imagine a really large service, and if you just change your scheduler and if you get 4% gain in terms of your bandwidth, that's a huge gain. So seems to sometimes help at least. And this is another test that we were doing. We did recently. This is like a machine learning setup where we're running a GPU workload, right? So it's a really big machine, a lot of CPUs, and like a lot of GPUs, really expensive resource. And because GPUs are like so expensive and hot these days, everybody wants to like prioritize GPUs, right? But GPUs sometimes need these CPUs to manage them, right? I mean, it needs to feed the data, get the completion, and do something, right? And feed the data again. And if you induce scheduling latency in these steps, then your GPU utilization drops, right? So we found out that people try to because there are like so many CPUs mostly sitting idle. So if you leave them idle, GPU utilization is fine. If you try to load the CPUs, then the GPU utilization gets impacted, right? So people were not happy about that. So on the left side, around what's the 150K, that's the like IPS, right, or QPS. So without anything running on the machine other than the GPU workload, that's what we hit. And then if we use the CPUs for something else, right? And if we load the machine with a workload which actually use the CPUs in addition to GPUs, then the QPS for the GPU workload drops, which makes a lot of people really unhappy, right? Then we load a schedext scheduler, which is not that complicated, but does certain things to help in that situation, and the QPS goes up quite a bit, right? It's still a little bit lower, maybe a few percentage points lower, but it's a lot better than before. And just showing that, right? You stop the scheduler, the QPS drops lower. You run the scheduler, it goes up. So so this is showing that in these conditions, running new scheduler is obviously beneficial. So we are currently testing and deploying on 3 major workloads, and then across them, what we see is that we see like fair amount of gains single percentage point, which is pretty good for system changes. And then the common pattern that we see, like where these gains are coming from, is that one is better work conservation. So this really depends on the workload, but if you have like CPUs and threads, there's this kind of thing you can call a stickiness, right? If you keep a thread on the same CPU, you get better cache locality, right? When you come back to run on the CPU, your cache lines are likely to be, on the harder caches, nearer caches, so that helps. But at the same time, if you wait too long, right, then if you wait for your CPU to open up because it's busy right now, you may be, not missing opportunities to run on, another CPU which is idle right now, right? And the longer you wait, the more your cache locality decays anyway, right? So there's a balance between, you don't want to be ignoring cache locality completely, but you also don't want to be too sticky, right? So there's that balance. And for a lot of modern workloads and that we run, and on a lot of modern CPUs, L1, L2 cache locality doesn't seem as important as the default scheduler assumes. So kind of relaxing that parameter seems to help quite a bit. And the second thing that we see gain from is soft affinity. It's basically grouping workloads, similar workloads together, right? So if we look at machines, I mean, like personal machines are a little different, but I mean, if you look at machine in a production environment, there's a lot of things happening for like monitoring and management, right? I mean, there's constant like upgrade going on, like monitoring programs going on. So there's quite a bit of activity going on outside of the main workload. So if you group like these things into like as few CPUs as possible and run them as hard as possible on those few CPUs, while the demand changes over time, so you want to be kind of elastic with them. But if you do that, what you achieve is that you because these threads don't go around the system, builting all the cache lines, you improve the cache line, cache hit ratio of the main workload, right? So thereby, thusly you increase the bandwidth of the workload more efficiently. The main workload ends up executing more efficiently. So soft affinity seems to help a lot, right? Now we are kind of trying to figure out a way to figure out like what to group together automatically so that they can stay as hard as possible on as few number of CPUs as possible. And per workload customizations, like going back to the machine learning example, right? If you know which threads are latency critical, then you can mark them, and then you can guarantee that those things always get the CPU whenever they wake up, and even try to make sure that the caches are as hard as possible for them, right? So you can have like these targeted optimizations, and of course like trying out different heuristics, right? In some cases, sometimes you just have to guess, and then heuristics, as they naturally are they're never perfect for any given workload, right? So if you have like a lot of parameters, then you can try a lot of different strategies. You can sometimes figure out performance gains. So one example scheduler that we are deploying in the fleet is called SCX layered. So SCX is just a prefix that we are using for all these schedulers, and layered is that it's kind of dumb, but the main goal of this scheduler is enabling ad hoc experimentation, right? So if you have a workload, right? I mean, someone walks up to you and hey, I have this workload. I want to run it better, higher performance, whatever, right? Higher bandwidth, more consistent latency, right? But they give you like a basic details of their workload, right? Or you have an idea and you want to verify it, right, against a workload that like going from there to write a full scheduler and then to experiment the ideas. And these are like a lot of different steps, right? It can take quite a while. So the idea behind SX layered is that give people an easy way to try certain simple things, but in a really flexible manner. So you basically just write a like JSON file describing, these threads belong to this layer or this group, right? Other threads go to this layer, and for this layer, use this policy, right? For that layer, use that policy, right? And that way, you can kind of really quickly iterate different configurations, and then find out what works and what doesn't. So this is two of the deployments are using this thing. So this is what the configuration looks like. It's just a JSON file. No need to actually read it through, but what it's saying is that this is a batch group. The single prefix is this, right? And the nice level is below this, and then you use these CPUs to target this utilization, and then you go to some other group is like immediate, like high priority group, and then you match these conditions, and those are the high priority ones, and then you give them CPUs as soon as possible, right? That's what it's saying. But you can see how easy it would be to tune these parameters and change your policy to find out what works. And it prints something like this, right? I mean, it shows how many CPUs are allocated to which group, and all that, and the statistics, so that you can understand what's going on. So up until now, I think we have about 4 or maybe 4 schedulers, which are not complete toys. So we have like this really simple schedulers, which are just examples. And then we have like 3 or maybe 4 schedulers, which are more serious, right? They're not quite fully mature, but they are already useful for specific use cases. And what we learned over time is that it takes quite a while to ramp up to write your own scheduler. And the reasons why was that these are the reasons why it's not sometimes it's a little bit challenging at least. So the challenges in writing schedulers, like the framework is all there, it's completely safe. You cannot crash your machine. Whatever you write, that's not going to crash your machine. Right? You wrote it, it might not work. Then you do timeout, and you do give back your machine after some seconds, right? But in like writing a working scheduler, there's some challenges still. The first one is that BPF is sometimes can be a little bit challenging. Who here have the experience of writing BPF programs that are not trivial? I'm sorry. So I mean, it can get really frustrating sometimes, because it's not like it's very far from like a modern, fully developed programming environment. It's constantly getting better, but there are still some challenges that you have to overcome. So that seems to be one of the barriers. And another thing is scheduling as a problem space is a little bit different from other problem spaces. Not because it's singularly special, but it's just it's a problem space which is distinct from others. So you just have to learn things, right? You have to ramp up on the area to be able to write something useful or interesting, right? So that just takes time. And another thing was that we tried a lot of different things. For example, one thing that the kernel default scheduler, the kernel scheduler does is that there's a single queue per CPU, right? So each CPU is scheduled separately, and then there's a load balancer balancing them, right? And this has its pros and its cons, right? I mean, the pros is obviously that it's easier to do manage stickiness, and also your operations are per CPU, so cache line bouncing is less and all that. The downside is that it's really difficult to make a larger scope decision, right? So the only way to make larger scope decision is through the load balancing. So one thing that we tried is that sharing a queue between some group of CPUs, and that actually worked out really well. So if you remember our first example, that example was sharing a single queue across the entire system, right? And even that works relatively okay on single S3 cache CPUs, because like modern CPUs are really good at communicating on die. So we are trying things like this. So I mean, what's the optimum like mapping between queues and CPUs, right? And one thing that we really liked was that mapping queues to S3 caches, right? Whenever you have like multiple S3 machines, you get put a queue on a single S3 domain and then load balance across them. And that's relatively new to what we used to be doing, and it kind of introduced the new problems where load balancing between queues which have multiple CPUs in them have like its own kind of mathematical problems in terms of calculating load and comparing them. So you're just facing these new problems because you're trying new things. So that takes a lot of time too. But there's also the fun part, right? So you get to solve new problems. So upstream and adoption. So it's not mainline yet. It's not landed. The first posting was over a year ago, I think so. But yeah, we are still iterating, and we're hoping to land it, in mainline in the upstream corner in the future. Don't know when, but we're working toward it. And at Meta, it's basically available in most of our machines. And in terms of so the kernel feature is available in most of our machines in the fleet, and we are in the process of deploying schedext schedulers to a few fairly big workloads, and we plan to keep expanding that. And Google has their own scheduler framework called Ghost, and with that they're experimenting with in a similar way with their workloads, and they are planning to port Ghost schedulers on top of schedext. And Canonical is investing resources to experiment on schedext enable kernel. So they have they have an engineer who's spending a lot of time on it, and they have a separate branch of the kernel which supports it, and they're it's likely that they will have the ongoing investment into schedext. And there are other efforts are also in progress. After this session, maybe 1-2 sessions away, there's a presentation from Chang, and he will talk about like Igalia's effort on schedext. So that's definitely one of the efforts that they're making, who's adopting schedext. So and it's available for multiple packages, multiple distros. So there's an active and growing community around schedext. So if you go to the Git repo, it has which should be fairly easy instructions that you can follow to install and try it out, and to develop it. And there are links to other resources, and there's also a Slack channel that we all hang out. And if you join and just ask something, yes, one of us will answer your questions as soon as we can. So it's fairly welcoming environment. So if you're interested in working on schedulers or find out how we are using it, what kind of numbers we are seeing, just come join and then ask us. We'd be happy to share. Yeah. So that's the end of my slides. I'm not sure how question is gonna work. Can you do questions? I cannot hear you. I think you're muted.
Okay.
Okay. Yeah.
Okay. Can you hear me now?
Yes, I can hear you.
I'll repeat the question. Yeah. Any questions?
Yes. So can you hear me, Tejun?
Yes, I can hear you.
Okay, so given that it's BPF, I'm sure that there's a lot of control over what data you can access from other parts of the kernel related to your threads, and the amount of such information that you can use for making scheduling decisions. So could you try to comment about that? Is there any limitation in that space? Is there things that needs still improvements with schedext, or where are we with this aspect of the work?
Let me repeat the question just so that I understand it correctly. So you're asking whether there are limitations in terms of like information available to make scheduling decisions because
Yes.
it's in BPF. Okay. We don't really see that. Let me think a bit. But I don't think that never has been a problem. So for example, right? I mean, all these scheduling callbacks. Let me go back to the slide, the first one. Let me see. Right, this guy. So if you look at like the in-queue callback, right? You get struct task struct P, right? You get the pointer to the struct, right? So once you have P, BPF is now mature enough that you can safely access most of its fields. So you basically have maybe not the same, but pretty close to full access to whatever you want to access. So that this really never has been a problem. And also, if there are contexts which are not available to you, there are some of them, and it's really easy for us to add what's called BPF K-funcs, which are like a helpers that kernel can provide. So I can just add like SCX BPF, give me this information, right? And then the scheduler can just call that and get the information, right? So that never hasn't really been a problem. And on top, another thing is that kind of on the opposite side, like one thing that a lot of our application developers kind of ask for is that if you are somebody like working on say async execution engine, right, in a company like us or in any organization, right, that you have a lot more context than the kernel, right? I mean, so these are thread pools. The threads in the thread pools look all the same to the kernel, but the async execution environment knows that this guy is running high priority request from that guy, right, and that guy is waiting on that guy. So that the execution environment has a lot more context than kernel does, right? And the only problem is that there's no easy way to communicate that to the kernel right now. So one thing that we are planning to try, and that Google is already well ahead of us in terms of trying, is that experimenting, is there like having shared context between the like a schedext ext scheduler and then application runtime engine or application itself, so that application can say this guy is important for this time duration, right? I'm out of important duration, ignore me, right? I mean, so you can have like a lot richer and higher bandwidth communication between the application and the scheduler.
That sounds good. Yeah.
Any
Thanks.
questions?
I worry about the security implications of having a BPF scheduler. I mean, there's been a whole heap of CVEs around BPF and having it enabled. There's a new Spectre variant that came out last week or the week before. They recommend turning off BPF for that.
Right. So yeah. So I mean, it's as secure as BPF can be, right? And the thing is that you have to be root to load schedext programs, right? So you have to have like so it's not secure. Like right now, we cannot allow a user to come with like a schedule implementation of their own and upload this for my application, right? Trust me, this is safe. So we cannot do that. So you have to be able to trust that the scheduler is not written by somebody who's adversarial to you. But that's kind of the same for most of BPF programs right now. So that's where we are at.
So any further questions?
So from your talk, you mentioned about one of the optimization from the scheduler is it can cause better session line utilization. And I'm wondering if you have to solve any problem regarding to architecture or microarchitecture difference and the hardware to make this optimization work.
Could you
Or
please,
is all abstracted away?
could you please just repeat the question, Tejun? That's comes on the recording.
I didn't quite follow the question. I'm sorry. Can you repeat it?
You mentioned one benefit of this scheduler is that it improves cache line utilization and processor. And I'm wondering if you have to solve any problem like in terms of difference in architecture or microarchitecture of the hardware, or this is all abstracted away by BPF?
Okay, I see. Okay, so I'm going to repeat that just in case. So the question is like whether like a schedext or BPF provides any abstraction against like a different microarchitectures and CPU configurations. Is that the right question?
Yes.
Okay, cool. So not in the framework itself. So the framework itself just exposes the interface that you can implement scheduler with, but the way that we are headed is that so a lot of schedulers are have BPF kernel code, right? Mated with their Rust user space code, which kind of interacts with it, and that just has a lot of benefits. Seems to have a lot of benefits in terms of like a Rust has really nice like a cargo, nice way of distributing shared library code, and then just easier to pull in other library code and all that. So what we are doing is that we are building these components as a cargo crates, like Rust library code, and they're all published in a crate called SCX utils. So the topology code, right? I mean, so in this case, right? I mean, if you want to have some idea of how the cache topology looks like on the machine, right? Then we have inside SCX utils, there's a topology part that you can just import and use, and then it'll tell you what the machine looks like, right? And then you can base your code based on that. So that part of kind of building a library to provide components for building schedulers with are still in early days, but we already have like 2 or 3 components, kind of non-trivial components that people can pull and use. So I think that's the way that we are going. Like, not that the framework itself is fairly bare, like it's or basic or fundamental, but like on top of that, we're going to have like a series of libraries that you can use to add this awareness relatively easily.
Thank you.
Okay, I think we've got time for one more quick question. We're going to wrap up. We're all good? Okay, well, thank you very much for your presentation. I think we could have a round of applause for this.
All right, thank you very much. I'm sorry that I couldn't be in person, but this was great. Thank you so much.